Next, we are going to look at measurable functions which are defined on measure spaces. So, they play play a role later on. So, we want to look at functions f which are defined on a set x taking extended real values and on x there is a sigma algebra S and a measure mu given on S. So, let us first define what is the meaning of the notion of almost everywhere. So, we say that a property P about the points of x is said to hold almost everywhere with respect to the measure mu. If you look at the set of points x for which the property P does not hold at x. So, look at all those points of x say that the property P does not hold at the point x. So, this is a subset and we want this subset belongs to the sigma algebra and mu of E is equal to 0. So, what we are saying is except for a set of measure 0 the property holds. So, that is why we give it a name that the property P holds almost everywhere with respect to the measure mu. Let me illustrate this with some examples. Let us take a function f and we will look at the statement that f is 0 almost everywhere. So, f is a function which is extended interval function defined on the set x and we want to say that this function is 0 almost everywhere. So, look at the set of points where f is not 0. So, what will that statement mean? That set where f is non-zero should be an element in the sigma algebra and its measure should be 0. So, x belonging to x say that f of x is not 0, that should be element in the sigma algebra and its measure. So, measure of can be defined only when the set is in the sigma algebra. So, mu of that set is equal to 0. So, that is the statement that f is equal to 0 almost everywhere will mean mu of measure of the set of points where f x is not 0 is 0. Let us look at another illustration of this. The statement that f is finite almost everywhere, what will that mean? So, that will mean look at the set of points where f is not finite, that means what? F is extended real valued function. So, it can take the value plus infinity or minus infinity. So, the set of points x belonging to x say that mod f x is equal to plus infinity. So, that is same as where either f of x is plus infinity or f of x is equal to minus infinity. That set is in the sigma algebra and mu of that set is equal to 0. So, saying a function f is finite almost everywhere means the set of points where it can take the values plus infinity or minus infinity is a set of measure 0. Similarly, let us look at two functions f and g, okay, and let us look at the statement that f is strictly bigger than g almost everywhere. So, f is strictly bigger than g almost everywhere. What will that statement mean? That means, the set of points where f x is not strictly bigger than, and that is the same as the set of points where f x is less than or equal to g x. So, the complement of that statement is f x less than or equal to g x. These set of points have got measure 0. So, saying that f x is strictly bigger than g almost everywhere with respect to mu means mu of the set where this statement is not true, and that is f x less than or equal to g x is 0. This concept of almost everywhere is quite useful when looking at measurable functions. So, let us prove the property that if f and g are two extended valued functions, say that f x is equal to g x almost everywhere mu, then measurability of one of the functions f implies the measurability of the other function g. So, f is measurable, s measurable if and only if g is s measurable. So, let us prove this property that if two functions are equal almost everywhere, then the measurability is not changed. One measurability of 1. So, let us look at f is from x to r star, g is also from x to r star, and we know that the set of points x belonging to x says that f x not equal to g x, this set has mu measure equal to 0. So, let us suppose f is S measurable. Okay. To show G is S measurable. So, to show that G is S measurable, let us look at G inverse of any interval I. Okay. So, G inverse for every interval I a interval in R star. Then G inverse of I, we want to show that, so claim is that this belongs to S for every interval I. Okay. And now, we have to transform this property, this set, into something regarding G. So, let us regarding F. So, let us look at G inverse of I is same as all x belonging to x such that G x belongs to I. Okay. So, this is a subset of the set X. So, what I can do? I can write this set as, so G inverse of I can write as intersection of, so x belonging to x, say that G x belongs to I and intersected with the set A, also union, so intersect with A complement. So, G inverse of I have intersected with A and A complement. So, it is a union of these two sets, x belonging to x, say that G of x belongs to I intersection A complement. Right. Now, let us look at the first set. So, this is G x belonging to I intersection A, and what was the set A? What is the set A? Where A is the set x belonging to x, where f x is not equal to G x. Okay. F x. So, let us observe, we are given that mu of A equal to 0. So, that automatically implies that A belongs to the sigma algebra S, and that automatically implies that the set x belonging to x, say that G x belongs to I intersection A, also belongs to the sigma algebra. So, this set also belongs to the sigma algebra. Why? Because this is a subset of A and A is a set of measure 0. So, this is a set of measure 0 and we have already assumed our measure spaces are complete. So, because of, so the implies this is so because the measure space x S mu is complete. So, we have made the assumption that we are working on complete measure spaces. So, that gives that shows the importance of complete measure spaces. So, this set belongs to A, and the other part A complement, on A complement f is equal to G. So, I can replace it by A complement. So, the set x belonging to x, say that G x belongs to I intersection A complement is same as the set x belonging to x, where f x belongs to I intersection A complement, because on A complement f is equal to G. So, that means what? So, G inverse of I is written as G inverse of I intersection A. So, let us just rewrite this statement again. So, what we are saying is G inverse of I can be written as G inverse of I intersection A union G inverse of I intersection A complement, and that is same as G inverse of I intersection A union F inverse of I intersection A complement, because on A complement f is same as G, and this is a set of measure 0, mu of this set is equal to 0. So, implies that this set G inverse of I intersection A belongs to the sigma algebra, and this set F is measurable. So, implies this set is in the sigma algebra, A is in the sigma algebra. So, A complement in the sigma algebra, intersection in the sigma algebra. So, this element belong to the sigma algebra. So, and this is a union of two elements in the sigma algebra. So, this implies that G inverse of I also belongs to the sigma algebra S. So, we have shown F measurable, F equal to G almost everywhere mu implies G measurable. So, that is the importance of measurable functions equal almost everywhere, but keep in mind we have used the fact that underlying measure space is a complete measure space. So, measurable functions, that means this says that if f is measurable, you can change its values on a set of mu measure 0 and still the function will remain measurable. So, another interpretation of this result is if f is measurable and you change its values on a set of measure 0 and call that function as g. So, that is measurable. So, that is a quite an important fact. Another application of this concept of almost everywhere is the following. Look at the sequence f n, a sequence of measurable functions converging to a function f almost everywhere. That is, the set of points where f x is not equal to the limit has got this set has got measure 0. Then the claim is then the f is also measurable. So, just now we proved that if a sequence f n of measurable functions converges to f, then f is measurable. And now we are saying that if f n's are defined on a complete measure space and f n converges to f almost everywhere, even then this property remains true. So, basically the idea is same as before. So, let us just look at how does one write a proof of this statement. So, we have got a complete measure space X S mu measure space. We have got a sequence f n of functions f n's measurable, f n's converge to f almost everywhere mu. So, that means, look at the set A x belonging to x such that f n of x does not converge to f of x. Then what is given to us is that this set A belongs to the sigma algebra and mu of A is equal to 0, right. So, now let us look at, so we want to show that f is measurable. To show f is measurable. So, once again look at for any interval I, look at f inverse of I. So, I can write as f inverse of I intersection A union f inverse of I intersection A complement, right. Now, on A, so we are given A is a set of measure 0. So, this is a subset of A. So, that has set of measure 0. So, this implies that f inverse of I intersection A belongs to the sigma algebra S, because this is a set of measure 0 and our underlying measure space is complete. And on this portion A complement f n is converging to f. So, this f I can write as limit n going to infinity of f n inverse of I intersection A complement. So, this set is same as this. Okay. And now, we know that f n on A f n's converge to f on A complement. So, that is a measurable set. Okay. So, this is a element in the sigma algebra, because on A complement f n is converging. So, if we restrict ourselves to A complement, then that must be element in the sigma algebra. So, both belong to the sigma algebra. So, this belongs to the sigma algebra S. So, the concept of almost everywhere when dealing with the complete measure spaces, we can exploit that property. So, this implies that if f n is a sequence of measurable functions converging to a function f almost everywhere, then the limit also is a measurable function. So, this emphasizes the property of something holding almost everywhere. Now, let us specialize the case when our underlying measure space is set is the real line. Then we have got two sigma algebras. When x is equal to real line, then we have got two sigma algebras. One is the Borel sigma algebra and other is the sigma algebra of Lebesgue measurable sets. And we have shown that the sigma algebra of Borel subsets is a subclass of Lebesgue measurable sets. So, when we are looking at functions defined on real line, taking values as extended real numbers, there are two possibilities to analyze whether the function is measurable with respect to the Borel sigma algebra or measurable with respect to the Lebesgue sigma algebra. So, there are two notions of measurability as far as real line is concerned, and so we will separate them out. So, we will say a function is Lebesgue measurable if the inverse image of every interval in R star is a Lebesgue measurable set. So, if the inverse image of every interval in R star is an element in is a Lebesgue measurable set, then we will say that function is Lebesgue measurable. And we will say a function is Borel measurable if for every interval in R star we will pull back its image, its pre-image in R is a Borel set in R. So, here is the difference. Lebesgue measurable requires that the inverse image is in the Lebesgue sigma algebra of Lebesgue measurable sets, and f inverse of phi in B R says it is the inverse image is everywhere is always a Borel set in R. So, obvious, because Borel subsets form a subset of R. So, it obviously clear that every Borel measurable function is also a Lebesgue measurable function, right, because inverse image of every interval if it is in B R and B R is a subset of L R. So, every Borel measurable function is also a Lebesgue measurable function. For example, let us look at a function which is continuous. So, if f R to R is continuous function, then it is going to be a Borel function. So, let us prove that every continuous function is a Borel measurable function and hence also Lebesgue measurable. So, f is a function which is defined from x is real line. So, f is a function defined from R to R and f is continuous. Claim that f is Borel measurable. That is, f inverse of any set E belongs to B R for every set say E belonging to B R. And continuity of a function can be expressed in terms of open sets. So, let us look at the class A of all subsets E belonging to B R such that this property is true, f inverse of E belongs to B R. So, what you have to show? To show saying that f inverse of E belongs to B R for every E in B R, it is an equivalent to saying to show that this A is equal to B R, right. And that is where we are going to use our sigma algebra technique. So, to show that A is equal to B R, note that A is already a subclass of B R, right, because of we are picking up sets in B R. So, to show that A is equal to B R, we have to show that B R is inside A. So, for that we will show two steps. One, open sets are contained in A, and second we will show that A is a sigma algebra, because once A is a sigma algebra and it includes open sets, it must include the smallest sigma algebra generated by open sets, that is B R. So, B R will be inside A and will be true. So, to prove these two facts are quite obvious because of the given condition. So, one, open sets belong to A. So, let U contained in R be open, F continuous implies that F inverse of u is open, and hence this means F inverse of u belongs to B R. So, what we have shown is if u is open, then F inverse of u is in B R. So, that proves, so implies that the open sets are inside A, and A is a sigma algebra, that is more straightforward. So, let us observe empty set is equal to F inverse of empty set, and so and R is equal to F inverse of R. So, both belong to A. Okay. So, because empty set and the whole space they are equal to this. So, this is obvious, empty set and the whole space belong. The second property, if E belongs to A, that implies F inverse of E belongs to B R, and that implies F inverse of E complement belongs to B R, and that implies, because this set is same as F inverse of E complement, okay, that belongs to B R. So, what we have shown is if E belongs to A, then F inverse of E complement belongs to B R, and that implies that E complement belongs to A. So, that means E complement. So, the class A includes empty set, includes the whole space, it is closed under complements. So, finally, let us show that it is also closed under countable unions. So, that means, so let us take sets E n belong to A, n bigger than or equal to 1, then look at, that means what we are given, that F inverse of E n belongs to the sigma algebra B R, because the property E n belongs to A means the inverse image is in B R. So, but that implies B R is a sigma algebra, that implies union 1 to infinity F inverse of E n belongs to B R. And now, a simple observation that this set is same as F inverse of union E n, n equal to 1 to infinity, that belongs to B R. So, if E n's belong to A, then F inverse of the union belong to B R. So, that means the union of n equal to 1 to infinity E n's belong to B R, belongs to A. If E n's belong to A, then F inverse of the union belongs to B R, that means the union belongs to A. Hence, we have shown that A is a sigma algebra of subsets of A, and it includes open sets. So, it must include B R, and hence this is equal. So, that proves that every continuous function from R to R is Borel measurable, and hence it is also Lebesgue measurable. So, all topologically nice functions, continuous functions become Lebesgue measurable on the real line. Let us look at some more properties. So, we showed that every Borel function is Lebesgue measurable. So, there exist functions first of all R to R star which are not Lebesgue measurable. So, to prove that, we have to only simply observe that there are sets. Okay. Let us go back and recall that for a function f from R to say R star, let us look at f equal to indicator function of a set A, okay, where A is a subset of x. So, recall chi of A is Lebesgue measurable if and only if A belongs to L of R. So, if you can produce a set which is not Lebesgue measurable, then the indicator function will not be Lebesgue measurable. So, the answer to this question, does there exist non-Lebesgue measurable functions, depends upon whether there exist non-Lebesgue measurable sets. And if you recall, we had proved the fact that the non-Lebesgue measurable sets exist. That question is related to basic set theory. So, if we assume axiom of choice, then we constructed non-Lebesgue measurable sets. So, assuming axiom of choice, one can claim that there exist functions which are not Lebesgue measurable. And by the same reasoning, one can ask the question, do there exist functions which are Borel measurable, but not which are Lebesgue measurable, but not Borel measurable, because every Borel measurable is Lebesgue measurable. So, that means for that, by the same logic again, if we pick up a set A which is Lebesgue measurable, but not a Borel set, then the indicator function of that set is going to be a function which is going to be Lebesgue measurable, but not Borel measurable. So, these two questions that whether there exists non-Lebesgue measurable functions and whether there exists functions which are Lebesgue measurable, but not Borel, get tied up with the fact that the Lebesgue measurable subsets is a proper subset of power set of R, and B R is a proper subset of the Lebesgue measurable sets. So, with that we conclude the study of properties of measurable functions. So, basically let me just recall, the measurable functions are functions defined on the underlying set X with properties that the inverse image of every set E in the Borel sigma algebra of extended real numbers, the inverse image is again in the sigma algebra on the domain space, that is S. So, this is a property about the inverse images of sets being in the sigma algebra S, and we will see that how this property plays a role in our further study of integration. So, we will do in the next lecture, we will start the notion of integration for measurable functions. Thank you.